All right, ladies and gentlemen, welcome back to another video with Mr. Kenton. This is for HL Chemistry, and we're plugging along through stoichiometric relationships. And we're actually going to be finishing up our conversation, our discussion with gases today by examining the ideal gas law, understanding how real gases deviate from ideal gases, and looking at how we can use the ideal gas equation to determine the molar mass of a gas. If we're trying to figure that out. And so the application of the skills that you should have or you should be able to apply once you've gone through this is to solve problems that relate to the ideal gas equation. And so let's just go ahead and dive right in here. So the ideal gas law, if you remember, we looked at Charles's law, we looked at Boyle's law, we looked at Avogadro's law, we looked at Gay-Lussac's law, and we were looking at all these different relationships of how the components or the measurements of pressure, volume, temperature, and amount of substance had a specific impact on properties of gases. Well, we can combine all of those things to describe gases using the ideal gas law. Now, the ideal gas law is going to be extremely helpful when we're dealing with conditions and circumstances when we're not at STP. And so we're going to use the ideal gas law when we're given moles or mass in a gas law problem, or if you're asked to solve for moles or mass of a gas. So you got PV equals nRT, where P is your pressure term, V is your volume term, N is the amount of moles, R is the ideal gas law constant, and T is your temperature in Kelvin. So there you go. P is pressure, V is volume, N is moles, T is your Kelvin temperature, and R is the universal gas law constant. Now remember, R has many different quantities based on the units that you're dealing with. So if we're looking at the R value of 8.31 joules per mole Kelvin, or the 8.31 cubic meters times pascals per mole Kelvin, that would be your R value that you could use there. Remember, there's also the one that's in where the pressure units are in atmospheres. That's the 0.08206. And you also have the one that's in torr and millimeters of mercury, which is the 62.4, right? But again, it's all dependent on the pressure unit is what's going to determine which R value you're going to use. And for those of you who are unit buffs or physics buffs, you should recognize that a joule is a Newton meter and a Pascal is a Newton per meter squared. So when you combine those terms, that's how you're able to come up with these individual units, right? So when you take that, that's how you're able to get those units to match up. Now, when you're doing problems, it's extremely important, always, like with any problem, that you use the correct units. Now, in this particular case, like what we're dealing with, like if we're using 8.31, then pressure has to be in pascals and volume has to be in meters cubed, which could prove a little challenging. And so, you just have to make sure that you can go from meters cubed over into liters so that you can use the appropriate values. Now, we should also be able to, like I mentioned, explain deviation of real gases from ideal behavior, specifically at low temperature and high pressure. And if you think about both of those circumstances, it goes back to some of the assumptions that we're operating under when we use kinetic molecular theory. If you recall, we stated that there are no attractive forces between individual gas particles, and we also communicated that the volume of the gas particles was essentially zero. Well, at low temperature and high pressure, both of those assumptions have to be ignored because attractive forces are going to start to play a significant role, as well as the particles occupying a specific volume that's not negligible is also going to come into play. So we talk about ideal gas laws, and when we talk about using PV equals nRT, we can pretty much uniformly use that because we're saying, all right, the gas is going to obey these laws. We're in these parameters that are going to allow us to make these assumptions, right? And so ideal gases, they obey all the gas laws, not just the ideal gas law, but Charles's law, Boyle's law, Gay-Lussac's law, Avogadro's law. Each of those laws can be plotted and obeyed by a gas if they're ideal. But like I mentioned in the previous slide, the real gases, they actually have attractive forces between them. So intermolecular forces are playing a part, that there are these interactions between the individual atoms or molecules as they're moving around in their container. Additionally, they also take up some volume, right? And those conditions become magnified at low temperature and high pressure, because at low temperature, the particles are moving much more slowly, so they have opportunities to have attractive forces between them. And if you're in high pressure, that means that you have a smaller volume, and so what volume you do have is actually being occupied. And if you're in a smaller volume, you're going to increase opportunities for your particles to collide with each other. Now, when we're talking about ideal gases, a gas is going to most behave like an ideal gas when we're at high temperature and low pressure, right? Because at high temperature, the particles are going to be moving faster, so there's going to be less opportunity for attractive forces to be formed. And at low pressures, that means the volume is typically larger, and so there are going to be less opportunities for those particles to hit each other, or for them to be consolidated in one space to where they're going to occupy more volume than what we would think. So just kind of keep those things in the back of your mind. Now, the last thing that I want us to take a look at is how we can use experimental values to calculate the molar mass of a gas from the ideal gas equation. Now, you might recall from AP Chem, we looked at this particular formula, but it's essentially a way to manipulate the ideal gas equation where you can solve for density and ultimately can solve for molar mass. So using density in the ideal gas law, the molar mass can be derived using the following expression. So M equals dRT over P, where D is density, R is the ideal gas constant, T is the Kelvin temperature, and P is pressure. Or you could say that the molar mass of a gas is going to be equal to the mass of that gas times the gas constant times the Kelvin temperature divided by the volume and times the pressure, right? And again, D is density and M is molar mass. And so these are just some different ways in which we can use the ideal gas equation. Obviously, we have the PV equals nRT. We have this where we can figure out the molar mass of a gas. We could rearrange this equation to where we could solve for density, where density is going to be equal to, let's see here, it'd be M times P over RT would be equal to the density, so the molar mass times the pressure divided by RT. And we've also looked at scenarios where we examined real gases and how they're going to deviate from ideal behavior at low temperature and high pressure. And so I hope this was a good review for you. I hope this is kind of jogging your memory on how to do things. Thank you guys so much for watching this, and I look forward to seeing you guys again real soon. Take care.